Thank the organizers for inviting me here. It is always wonderful to be here. So I'm going to give 4 talks here, so 2 today, 2 tomorrow. And the title is kind of a very brief introduction to ergodic theory, and it assumes basically no background. Today I want to talk about cases of kind of hands-on ergodic theorems. So in the setting of often called unique ergodicity, but we'll see what we're talking about right now. In the second talk, we'll prove the general ergodic theorem of Birkhoff and Furman, I think. And tomorrow, 2 talks. One is it is something which is not strictly speaking ergodic theory. It's a representation theory of semi-symmetric groups. It's a theorem of Howe-Moore on vanishing of matrix coefficients. And in the last lecture, I want to illustrate some of those, what's going on and questions in a certain family of dynamical systems which are homogeneous spaces, G mod gamma, where G is SL2R, and gamma is a lattice there. But I want to discuss the notion of entropy. Now all of that, I was trying to prepare those talks, and I wrote up lecture notes, so you can get them either from me, from the webpage, or from the webpage of the conference. I think Roman linked that. There are still typos, but things will be fixed. Anyway, so let's start from here. So the setting, which is very common, is that you have, oh, that's the better color. You have xt. So x here is compact. I'm not aiming at the greatest generality, so it's going to be a compact metrizable space. The particular choice of metric does not matter. And T is a continuous map from x to x. Doesn't have to be invertible, so just a continuous map. And in dynamics, we want to study the behavior of iterates of such a transformation. Before doing that, a few general remarks. So you can look at C of x, the Banach space of all continuous functions on x. Let's take, say, taking values in complex from x to complex numbers. F is continuous. You take it with the sup norm. And that makes it into a Banach space, and it's a vector space. And with respect to this norm, it is complete. It is also separable, which means that it has a countable dense subspace. So the separability only is an exercise. Now, we think of, now, by Riesz representation theorem, the dual space to that Banach space, the space of continuous functionals on this topological vector space, can be identified with the space of measures which are finite signed Borel regular measures on x with measure mu acting on this vector space by integration. So f, the function here goes to the integral of f du. So this is the functional which assigns numbers to functions. And what's important to notice here is that Okay, well, there is the dual norm. So the norm on measures which comes from this identification is the total variation norm. But more importantly, there is the weak star topology. So there is the topology coming from requirement that all of these viewed as functional measures. Let me just write weak star. Hope everybody's seen it, but if you haven't, just take this as a definition. Sequence mu n converges to mu in that topology that I'm interested in, if and only by definition for every continuous function, integral f d mu n converges to the integral of f d mu. Okay. And that's our standing assumption. So this is the weak star topology. Now, I'm going to be interested in unit ball here, but more specifically in the subspace of probability measures on X. So these are positive functionals normalized to be 1 on the constant function 1, equivalent to probability measures, positive measures with total mass 1. And this would be an important topology here. So what I want to say here as a fact that you can prove quite easily is that this space, while it is convex subspace of this vector space, it is also compact and metrizable in weak star topology. Therefore, it was enough to consider here sequences, and that has to do with the fact that C of X was separable as well. So this we're going to use. And now I want some definitions. Oh, colors arrived. So technical definition, if you have a sequence of points in X and mu is some probability measure on X, we say that the sequence like this is mu equidistributed if the probability measures which are built from taking Dirac measures at these points and taking an average, if they converge weak star to mu. Or equivalently, if for every f in Cx, the average of the values of the function along the first n elements of the sequence, which is exactly applying this measure to function f, if that converges to integral d. Okay. This is the definition. And here is a remark/exercise. It's all easy. It could have been given there. It suffices to check this thing for a family of functions which spans a dense linear subspace for any family of functions which spans a dense vector subspace of Cx. Well, why is that? Because if you want to check that this is true for arbitrary function f, you take an epsilon, then approximate this f by a finite linear combination of those. For each of them, you wait long enough so that you will get half epsilon of closeness, and then definition. Now I come finally to the transformation. So if I have xt, so for this first hour, xt always means compact metrizable continuous transformation. Okay, so this is that logical dynamical system. So this is given. Suppose that x in x is some point. We say that it is, and mu is some probability measure on x. Let's say that x is mu generic. Here the notion that we were introducing was that if the sequence of the consecutive iterates of, the images of x under the transformation, if that was mu equidistributed. In other words, it satisfies that you take these averages. Is that clear? The notion? So here is a remark exercise. If x is mu generic, well, it only makes sense to talk about mu generic points for measures which are t invariant. T invariant means that applying the theta mu gives you mu. Why is that? Because if a sequence is equidistributed, then the shifted sequence, so if you just drop the first term and put all the indices back, will also be equidistributed, which is, this is very easy to see here. And from that, you can conclude that if x is mu equidistributed, then t of x is t mu equidistributed. And this should be the same thing. Okay. Finally, there is, okay, maybe let's do an example. Suppose that x is the circle, R mod z. Then if you have any sequence of points on the circle, then it is Lebesgue equidistributed. So equidistributed with respect to the usual Lebesgue measure, which is like Lebesgue measure on the interval vector. If and only if for every non-zero integer, what do we have? 1 over n summation j equals 0 to minus 1 of e to the 2 pi I k xj goes to 0. Yeah. So this is, in other words, you take your x1, x2, x3, and so on, and you look at those points, and you think of those as complex numbers, vectors. You add them together. If the image has, you take the average, so if it gets shorter and shorter, and this is true for original sequence and also rescaled ones, then this is a criterion of being equidistributed. And the reason for that is that because the functions, let me call it fk of x, which is e to the 2 pi I kx, these functions in integer form well, they span a dense subspace. Of continuous functions on the circle. Well, this is just Weierstrass theorem, or Stone-Weierstrass theorem. because, well, the finite linear combination of those, they are just known to be full trigonometric polynomials, and they form an algebra which separates points. So, by basic Fourier analysis or whatever. So these functions are good enough. Any continuous function can be approximated by those. And this criterion tells you that for every one of those functions except for the constant one, you know, they average to 0, and 0 is exactly the integral of fk for k not equal to 0. For the constant function 1, the average will go to what it has to go, so there is no doubt about this. And we get to the first interesting dynamical system. So if you take S being R mod Z, and you have a transformation which maps x to x plus alpha, and now my alpha is going to be an irrational number. So the iterations of that transformation is what, well, I usually draw the thing which is 2 pi I of that. So this is turning by alpha, and you iterate that 2 alpha, 3 alpha, and so on. So what we want to say is that for every x in x, for every x in x is equidistributed with respect to the back measure. So if you take an arbitrary point and start iterating it, it approximates in Book-Star topology the usual back measure. And why is that? Proof, what we need to do is to check this condition, or if you got confused by this, I think you didn't, but supposedly you could, then you just take fk of x, which is e to the 2 pi I k x. K is an integer. And you look at the iterates, so you look at these averages for fkx plus fkpx plus and so on, fkn minus 1x. Now what this is 1 over n, here is summation j from 0 to n minus 1, e to the 2 pi I. Now, whom do we have here? We have x plus j alpha, and that was multiplied by k. And if you pull out the irrelevant thing, which is e to the 2 pi I k x from the summation, in the rest you have the sum of e to the 2 pi I k alpha, whatever this was, to the power j. So this is just a piece of a geometric series. So this call it W, and this guy call it Z. So what you have is you have 1 over n w plus wz plus and so on w z to the n minus 1. And this is w 1 minus z to the n over 1 minus z, and everything 1 over n. Now this z happens to be, because alpha is irrational, k alpha is never 0, this is not 1. Therefore, I'm dividing by something which is not 1, so this formula does make sense. Everything's okay. The numerator is bounded by 2 in absolute value. This is constant. 1 over n goes to 0. This is true for every k which is not 0. So this is a fact. Now, one more definition. That is xt, or definition or theorem. Let's put it as a theorem. So the following conditions are equivalent for xt, which is some topological dynamical system. One is that there exists unique invariant measure. Probability measure on X. Okay, in a few minutes I'll show that every topological dynamical system has at least some invariant measures. And this set of invariant measures will play an interesting role. So this is the situation where this set is a single when this is just one. Two, well, let's give it a name. It's mu. Two, every point, every x in X is mu generic. So this generic for some particular mu, this mu is going to be the same mu. And three, for every continuous function on X, the averages converge for every x, and in fact uniformly, to a constant function. Converges being uniform. This constant is going to be the integral of f with respect to this mu invariant measure. Okay, so I can write it just integral of f. So these conditions are equivalent, and when they hold, we say that xt is uniquely ergodic. And what we argued here was that if alpha is an irrational rotation, then it is uniquely ergodic. Because we proved that every point was generic with respect to the bed. So this is uniquely ergodic. Now, let's prove this theorem. There are actually many proofs of this, but well, several at least. Along the way, let's prove the following useful fact. So in the notes, I actually wrote another proof, but here, let's take a shortcut. So here is another theorem, and I admit I'm always embarrassed which name should go with this. There are four people with different combinations. It's Krylov, Bogolubov, and Markov, and Kakutani. And for this long an argument, you might argue it's a little over, too many great people. But it's like Cauchy Schwarz, It's very easy in equality, but it is so useful that it needs a name. But so suppose that you have x and t. And again, this is the logical dynamical system, right? And suppose that you have a sequence xn. And suppose that you have some sequence n going to infinity. This is a sequence of integers. And suppose that you are looking at 1 over n of the Dirac measure at xn plus Dirac measure txn plus and so on t n minus 1. So I'm taking a segment of an orbit, of a t orbit, consecutive elements of a t orbit, and we're taking that. No, sorry. I should have done this many steps. So this average corresponds to how many terms there are. Suppose that this converges to mu in weak star topology, then mu is T invariant. Let me write the T invariant measures as this. So T is, sorry, I know it's not the right quotation, but T is implicit here, but that's all. But as a corollary, this space is not empty. Why? Because the space of probability measures is compact in weak star topology. It's also metrizable. So if you take just any sequence, take just a single point x. So this sequence is going to be single point x, and take consecutive iterates and look at the averages. Okay, this is some sequence of measures. There is a subsequence which converges. So let that be already the subsequence of measures. It converges to something. This something is going to be invariant. That's what it said. Is that clear? Okay, the proof is very easy. So the fact that this converges says that for every function f, no, but let's look at every function f, and let's look at the difference between integral of f with respect to d mu and the integral of f with respect to the shifted t star mu. Okay. Now this is the limit when n goes to infinity of, okay, these averages. This one xn, subtract. Now it's same normalization, so I'm subtracting in more or less the same line. And here this is that. Okay. While looking, this difference is just this thing. All the terms here cancel except for the first and the last one. So it's a limit of these. And this goes to 0 because my function was fixed, and n go to infinity. And therefore the limit equals to 0. But if you have two probability measures and they agree on every continuous function, they are the same. Okay. So this is a T invariant measure. So we come back to our theorem. So what am I supposed to prove here? So let me, in this theorem, let me just rewrite this as the space of invariant measures on X is the singleton. So I want to show that 1 implies 3. 3 implies 2 is obvious. Just think of that. So 1 implies 3 is the main point here. So I'm actually going to show that this converges to that particular constant. So suppose if 3 fails, then there exists an f continuous function, a positive epsilon, a sequence, infinity, and some points, such that these averages you don't want to get confused later, right? As ni and xi, such that these averages differ from the integral f d mu by more than epsilon. and epsilon is positive.
What is mu?
Mu is the, so I'm assuming 1, this is the unique invariant measure. Okay, yeah. In my formulation, okay, let's, yeah, so we're going from 1 to 3, so if I show that it converges to this constant, I'm even better than what I wrote. It's going from this up where you take off from some unknown. But if the convergence does not hold, or at least if it is not uniform, then there is a sequence of points which violates it by at least epsilon. But this is impossible. But passing to further subsequence, we may assume that the average is 1 over nij. Well, let me just suppress the passage to subsequences. Delta xi plus delta txi plus epsilon plus delta t and I. And this converges to some nu, right? Whatever it is doing, by passing to a subsequence, it should be able to converge to something because the base of probability measures is compact. It's metrizable compact, given sequence, there is a subsequence. Everything is very easy, just diagonal process. Okay, but according to the exercise that I erase, anything like that, any weak limit of this is going to be an invariant measure. The set of invariant measures was assumed to be a singleton, so this is going to be mu. But it cannot be mu because this convergence, this is a weak star convergence, would assume that these things converge to 0, the difference. But they're not. Does it make sense? Okay. I guess I'm asking those people who haven't seen it, but maybe there are no such people. So this is the kind of tricky direction of this theorem, because the whole theorem is not difficult. It's just amazing that things work out that way. But they are quite easy. So if there is only one invariant measure, then for every continuous function, the average is what's called the ergodic averages. The word ergodic should be introduced in a minute. Converge to the integral of such function against this invariant probability measure. Now, going through these other things is also easy, because if you converge to, if such averages converge to a constant, and you take any invariant measure, then integrating the left with respect to that invariant measure would be, I'm not going to write it, is going to converge to the integral of that constant. But integral of this is average of integrals, and each of them is the same thing because I said I'm taking it invariant measure. So an integral of f with respect to any invariant measure is going to be this constant. So every two invariant measures should give the same constant when they integrate any continuous function. That means that there was only one invariant measure. So this is going from 3 to 1. Okay, I'm going to use this theorem. Now, what I want to say is that the irrational rotation is a very easy example of dynamical system which is uniquely ergodic. But there are many others which are much more interesting. So now I have short time to describe an interesting example of a dynamical system. Well, it was also interesting here. But instead of, so in the following example, in the following example, you take, instead of a circle, you take a torus. Let's say two torus. So x equals R2 mod Z2 or R mod Z times R mod Z. Well, on the two torus, there is a system which is very similar to the one that we just described. Instead of an irrational rotation given by a single coordinate, you can do a rotation, or you can apply a shift on this compatibility group by a vector consisting of alpha 1 and alpha 2. And assuming that alpha 1 and alpha 2 are irrational and also not independent of rationals, you will get unique ergodicity, and this is pretty much the same proof as the one that we give. So this is not an interesting example that I'm trying to describe. The interesting example comes from a construction which is called the skew product. So it is the following. I fix alpha, which is a single irrational number, and I take a transformation of the two torus, where on the base we're going to use an irrational rotation. So here we're going to go by alpha every time. But in the second coordinate, we're going to rotate not by a constant amount, but by an amount which depends on the place where you are standing. So there are circles here about this, and this is the transformation that I have. Okay. More generally, one can take xt to be some logical dynamical system which is, let's say, uniquely ergodic base. And you can take a function from x to the torus, which is going to be continuous, so that the whole thing is going to be continuous. The following line is going to be well-defined continuous map. So this is going to be a continuous map from x to R mod Z. But now you consider a new dynamical system where x hat is x times the circle. And t hat is a map which takes xy to tx, comma, and here in the y coordinate, which is the circle coordinate, you shift by phi of x. Okay, so this was an example of such a thing where the base itself is an irrational rotation and the function phi is just identity function from circle to circle. So the claim is that this is a uniquely ergodic system. So the theorem, it's very nice theorem. All of that things, I really recommend this beautiful paper of Furman. Now I forgot the year exactly. It's a while back, maybe 60. Which is called, I have it written up somewhere. Well, let me know. It's a really beautiful, beautiful paper. It is from 61, and it is called strict ergodicity and transformations of the torus. And in there is this little gem which says that if xt is uniquely ergodic, phi from x to r mod z can be any compact group, in fact. And instead of the circle and fiber, and x hat p hat is as above. Should I say as on the left? Then if the measure, which is so this was a uniquely ergodic system. So let me give a name to its measure, mu. Okay, it has the unique invariant measure. So if mu times the Lebesgue measure, so this is Lebesgue on the circle, if that is ergodic, I have to explain the term. Then x hat t hat is uniquely ergodic. And in particular, there is the equidistribution. Okay. Now, I'm going to prove this theorem, and I'm going to explain everything there. So here is corollary. This transformation, which some people call Kirstenberg transformation, xy goes to x plus alpha, y plus x, is uniquely ergodic. So by the theorem, it is true once you know that the Lebesgue measure times Lebesgue measure is ergodic. I still haven't defined this term, which is pretty funny if you're talking about ergodic theory. But let's postpone it to the very last minute. So we'll check that this is uniquely ergodic, and that the Lebesgue times Lebesgue is ergodic. Then this is uniquely ergodic by this theorem. What I want to say is that the conclusion of this is that corollary is that the sequence that if alpha is irrational, then the sequence n squared alpha mod 1 is equidistributed. And now this is already very interesting. So I think I think it's more or less at the same time, maybe by Kronecker, don't quote me on this, that people started talking about equidistribution on the circle, and it became immediately available that if you take an irrational rotation and translate, then things get evenly spaced, and you average things as you should. So we proved that actually, but I think it is not a big surprise. The point is that irrational rotation is something which every point behaves like every other point. If they were at distance so and so at the beginning, then they continue doing the same thing. And if that point was, placed everything equally, the other point should, at least nearby points should do similar things, and you can argue. So there are many ways of arguing why isometries on a compact space would behave very nicely. But here, the fact is that you're looking not at consecutive iterates of the transformation, but you're looking at the irrational rotation along squares. And by the way, you could do cubes or any other thing. In fact, you could put here, instead of this expression, you could put any polynomial where at least one of the coefficients, non-constant coefficients, is irrational. And it is also going to be equidistributed over the circle. And this is quite surprising. Now, this was discovered by Weil. So this Weil. But this is a very nice angle under which you can see this from this purely dynamical standpoint. And how do you see this? So Kirstenberg argues like this. Look at this weird transformation. Start iterating it. So this was the transformation t hat that we're talking about. So if you take t hat to the power n, apply it to x, y. Now what happens, let me do it slowly. So if I take x, y, and apply 1 t hat, I get x plus alpha, y plus x. If I apply another t hat, I get x plus 2 alpha. It's everything mod 1, so I'm not. Now y plus x plus alpha. So 2x plus alpha. So x's get accumulated. But this is not the axis which is interesting here. So you go on. Then you get x plus 3 alpha. Now I have here y plus 2x plus alpha plus x plus 2 alpha. So I have y plus 3x plus alpha plus 2 alpha. Okay, and if you go n steps, then what you get is x plus n minus 1 alpha. Okay, nothing much here. Y plus nx. But here, alpha plus 2 alpha plus 3 alpha plus n minus 1 alpha. And this is arithmetic progression, which has a formula like, okay, am I fine here? I think I'm pretty safe. Okay. So I'm trying to say that t hat n of x, y is this expression.
There is some inconsistency with the n and n minus 1.
Yeah.
I think it's x plus n alpha.
Here. But you agree that this is not important. It's by definition not important. Once you quote some authority, then you do it on the board. So anyway, it is this. So what happens is that let's do. I did the calculation in these notes, but I'm not going to open it in the right place anyhow. So if alpha is yeah, sorry. If you take beta to be, so if you did the whole thing instead, so suppose that I was trying to prove this theorem for beta here. So my letter beta. You take T star with alpha being 2 beta. So this is twice beta. So this is n times n minus 1 beta. And then you apply the equidistribution of T hat star applied to, I can use any point I want. That's the whole thing, right? So the point I'm interested in is the point alpha comma 0. If you do that, then things, so y is 0, x is alpha, and now you consider the function of 2 variables, which is just a function of this. You take a function of a single variable, you pull it back as a function of 2 variables, and you get that the averages apply to this. On one hand, they have to converge to the integral of capital F, dx dy. But this is going to be just the integral of f on the circle. And this is going to be the average capital N of so you get the equidistribution of n squared beta, from the fact that T hat equidistributes on the two torus. So the trick here is you want equidistribution along some finite sequence on the one torus, and the way you conclude that is you are looking at a different dynamical system in which, well, this so-called skew product, in which something funny happens in the fibers, but you will use regular iterates of a more complicated transformation to conclude what you wanted about the more complicated sequence. So this is the beautiful trick. Okay, so I do want to give a proof of this. So we derived the conclusion, but we do want to analyze this system. So there are a few observations which go into this. So first of all, the definition and measure U. It's always going to be about T invariant measures, but the probability measure on X is T ergodic if the only T invariant, or T mu almost invariant, okay, let me write the following. If the following is true, take any measurable set and assume that this set is T invariant from the standpoint of the measure. In other words, the set is not different from its T translate, at least if you ignore null sets. Ergodicity means that this happens if and only if mu of E is 0 or mu of E is 1. If mu of 0 is, if mu of E is 0 or mu of E is 1, then this is trivially true. But a transformation or the measure is ergodic if this implication works. And what this means is that it's impossible. So what happens if your transformation is not ergodic? It means that there is a set, a measurable set, which is non-trivial from the standpoint of the measure. So E and E complement have both positive mu size, and E is basically T invariant, or up to null sets which I'm not drawing. The transformation keeps this to itself, and then it will keep the other side to itself. So if your space can be decomposed in some non-trivial way. So this is ergodicity. And the cute thing is that if you start from a topological dynamical system, the set of extremal points of the space of T invariant probability measures. So there is this space of probability measures on X. This is convex compact subset in the weak star topology, as we said. Inside of it, by Krylov, Bogolubov, Markov, Kakutani, there are always invariant measures. The set of invariant measures, this collection, is not empty. it's very easy to see that it is closed, so it is compact. It is also convex. If you have two invariant measures, then the convex combination is also invariant. Now, this is a convex compact subset. You can look at its extremal points, those points which are not middles of an interval contained in your convex set. So extremal points is something, just a notion which is defined in terms of convexity. What this theorem says is that the set of extremal points is precisely the set of ergodic measures. So something which is very intrinsically measurable is described as notion of extremality related to other sets. So it's a nice connection between topology and this. I know that I'm slightly over time. Let me just write it.
We started late, so
okay, I'll take an extension of a minute or so. So why is this true? One direction is really easy. So if, let's say, if U is not ergodic, so it is invariant but not ergodic, then there exists a measurable subset such that mu of E is positive and mu of E complement is positive. I can define normalized probability measures. Mu of E is going to be just the normalized restriction of M to E. In other words, mu of E of any set is mu of this divided by that. Okay, so it's a probability measure. And I can also write the similar thing for E complement. And I want to notice that mu is a convex combination of this with that. And if E is T invariant or T mu invariant, like in that sense, then actually even only if, then mu E and mu E complement are also T invariant. So it's something trivial to check. But what I'm trying to say is that if mu is invariant but not a ergodic measure, then it has, the world can be divided into two spheres of influence, E and E complement, and then U gets a presentation as a convex combination of two things, each of which is T invariant. So this implies that if this is not ergodic, then U is not extremal point of the space of invariant measures. Okay. The slightly more delicate direction is the opposite one. I'll do it after the break. But after that, we're going to prove, we're going to switch to measurable setting completely and prove Birkhoff's ergodic theorem, which says that one consequence of that would be that if you look at any ergodic measure, then mu almost every point is generic. Thanks.
thank you very much. So please ask questions. Are there questions? Okay. No official questions? Then maybe over coffee, right? So there's coffee on the 8th floor, and we resume in half an hour.